Okay, so now we're moving into the term 2 materials that we've done, the fluid mechanics stuff first. And as you hopefully remember from fluid mechanics, uh, it uses a lot of Physics 1 stuff, right? Either free body diagrams to calculate buoyant forces or kinematics describing the flow of water. So this section, if you've forgotten Newton's laws and forces and how to use them, this section is what you review it for. So this question is going to look a lot like a Physics 1 question, I think. But it uses stuff we covered in fluid mechanics, so it's good practice for that too. So first we have to draw a free body diagram. We have a boat and an anchor, and they're floating, which is generally a good thing, right? We're told the depth the anchor is at, the depth of the water in total, and the mass and volumes of the anchor, and the density is that of water. So we need a free body diagram. That's always a good place to start. If this is our anchor, we need to figure out all the forces that are acting on it. And I think the first one is the most obvious, right? It has mass, therefore there is a weight force. Right? You can call that the force of gravity, you can call it mg, whatever you want. There's a weight force, though. Second thing is, there's a cord attached to it, right? So there has to be a tension. And then finally, the last one is the only tricky one, but only because it's not something from Physics 1, right? It's the whole point of the chapter. It's a anchor submerged in water, so the water is pushing up on it. Not enough to make it float, obviously, but there's a buoyant force. It's also straight up. And that's, actually, I'm going to move that tension to the other side to make it fit. But that's really it, right? Don't overcomplicate things. But since it's a fluid mechanics question, and if you kind of read the whole thing, you know there's gonna be a buoyant force, so you better have that one drawn there. I think the weight and the buoyant force are guarantees on that, and the tension is pretty obvious as well. So I mean that right there is right a three points of this question, and everyone I think should get that. So part B, we have to calculate the magnitude of the buoyant force, and from part A, you might think that you're going to do like a Newton's laws thing, right? It's everything's at rest. So we know that the tension, the buoyant force, and the weight force all vector sum to be zero, right? No acceleration. But we don't know the tension or the buoyant force, so we can't use Newton's laws yet to find the buoyant force. But we know there's a definition of the buoyant force, which is on the equation sheet as rho times V times G. And all you need to do is just kind of identify what these mean, right? This density is specifically the density of water, not the thing in the water, right? So 1,000 kilograms per meter cubed. The volume is the submerged volume. In this case, since the anchor is completely submerged, it is its complete volume. Right? 6.25 times 10 to the negative third meters cubed. And I've given both those numbers in SI, which is very nice of them. And then G is just what G always is, right? 9.8 meters per second squared. So you plug all those in, and you will find that you should get like 61.3 newtons. Right? And you should have 3 sig figs, it looks like, for this question. So that's part B. Now, for part C, we can actually do that Newton's law stuff, right? The buoyant force is a force that we know a bit more about, so we can start with that without using Newton's laws, and then we can find tension sort of using the process of elimination. So for part C, right, Newton's second law tells us the sum of the forces equals mass times acceleration. In this case, it's not accelerating, so it's equal to 0. The tension is up, the buoyant force is up, and the weight is down, right? So I give positive and negative signs appropriately. So we can solve for tension equals the weight, mg, minus the buoyant force, which is that rho vg number. We just calculated it. So we plug in numbers. We know the mass of the anchor, and so we're just going to get that it is 429 newtons of force in the tension. right? So it's not supporting the whole weight because of the buoyant force, but it's supporting most of it. All right, and so finally, because this is actually a pretty fast question, right? Finally, the last part of this problem is we're told the bottom of the boat is a little bit submerged, right? They've drawn a little bit of it underwater. And we're asking the question now, we lift the anchor up into the boat. Does that little bit of submerged amount get bigger, smaller, or stay the same? And they're not asking you to do any calculation, but you should be sort of referencing and keeping in mind the idea of what a buoyant force is, right? The buoyant force on the boat is based on how much of the boat is beneath the water and how much it needs to be supported, right? How much it weighs. So currently, you need to support the weight of the boat and the anchor, and the total amount of volume underwater is the volume of the anchor and that little bit of volume at the bottom of the boat. When you raise the anchor out of the water, now that volume is no longer under the water. But you still have to support the weight of the boat and the anchor together. So the volume that's at the bottom of the boat that must be submerged has to go up to sort of replace the volume that the anchor was occupying under the water. So that way the buoyant force stays exactly the same, right? So the answer has to be that the new depth, d prime, has to be bigger than d. So you should put that d prime is greater than d, because we need to sort of replace the volume lost when the anchor was raised out of the water to keep the total buoyant force the same. And therefore the boat has to go down a little bit.